All right. Hello. Today we're going to be talking about this vending machine that we have here with priority encoding. All right. So this is very similar to the project that we have done last time, but there are a few key differences. So in our last project here, as you could tell, we do not have a priority encoder. Rather, we have a mess of wires here that are giving us our 4-bit representation of nickel, dime, quarter. In this old design, we are working with only 4 bits, but now in this new design, we are working with 8. So our adder and our register and our comparator all have to be set to accept 8 bits. And then finally, of course, we are now working with pennies. So in this project, we had no pennies. So our nickels were represented as 0001, but now that's going to be the value of a penny. So I'm going to go ahead and show you how this machine works. Right now, I have the price set to $1. This is in hexadecimal. So 6 times 16 is 96, plus 4 is 100, or $1 in our case. I'm going to just make sure everything is reset. All right, so I'm going to go ahead and add 75 cents in quarters. So that's going to be 3, 1, 2, and 3. I'm going to go ahead and add a dime. So now we're at 85 cents. I'm going to add a nickel to make 90, add another one to make 95. And then finally, I'm going to add 5 pennies. So 1, 2, 3, 4, and 5. And as you can see, our vending machine is available for us to select a product. And I can hit a product select and get my whatever snack I want. But before I do that, I'm going to add one more penny to make it 65. And as you can see, when I hit product select, I did not get any change back, which is also another main difference between our last project where we had this subtractor here to help give us the difference between the set price to figure out how much change we get back. So that is not present here in this design. Okay, so let me go ahead and show you our priority encoder. As you can see here, this is our design. If I have a penny set, that is obviously just 00001. We have a 1 in the least significant bit. All right. And then a nickel is, of course, binary 5. A dime is 10. And a quarter is 16 plus 8 plus 1, which is 25. But if I leave quarter left on and I go ahead and select a dime, the binary values do not change. So this is what high priority in encoders is, all right? So an encoder outputs a binary number that is respective to any single input that we select. But with high priority, we will always output the highest input value that is selected, despite multiple selection inputs being made, all right? So if we were to accidentally, say we wanted to insert in a quarter and, oh, whoops, you accidentally slipped in a dime. Well, at least the quarter has still been read and it's not going to change at all. So there we go. Nobody's going to be upset, if they accidentally slip into change 2 dimes or a quarter and a dime at once. So that's the value of having priority encoding. So, and then also having it as a device just simplifies everything so much. As you could see here, even with 4 bits, things get a little bit complicated, but with 8 bits, this would be twice as more complicated, I would assume. So having it just set into a device just simplifies everything for the eyes to see and might make it easier, if somebody had to manually open the vending machine and fix the priority encoder or, replace it, it's probably a lot easier to do. All right, so how might this pattern be extended to 16 bits? And what difficulties might arise as the number of bits increase? So if we wanted to extend this to 16 bits, obviously we would have to increase our splitter that we have here so that there is 16 values. We would have to change our adder, our register, and our comparator to all be able to accept 16 bits, all right? And I would assume that if we're working with 16 bits, we would be working with a lot more high-end items within this vending machine, because with 16 bits, we could have values worth all the way up to $655.35. All right. So, you might want to include possibly a dollar, maybe a $5 bill, a $20 bill, and a $100 bill. So that would complicate the priority encoder, quite a bit. So another difficulty that arises is the fact that you would need to increase your propagation delay with the more bits that you are working with. You could see here in our last project, we only needed 12 NOT gates for enough propagation delay so that the adder can update before moving into our D flip-flop here. But here I needed to use more than 12. I'm using 20 here. You could probably get away with 16, but you would definitely need more propagation delay when you increase the number of bits that you are using. So should the USA still mint the penny? That's a good question. For this vending machine, it'd probably be crazy. Hopefully you're not putting $655 worth of pennies to try to get your product. The penny is kind of pointless, especially now since we're using cards for everything. But, change is change. So what are the advantages of communicating the register values and the price in hexadecimal rather than binary or decimal? You could see here at this comparator, we're comparing two values. That is the value set here in the register and the price that we have set. All right. Now, if we had these both in binary, we would be comparing two 8-bit binary values, which would take more time than comparing two hexadecimal values. So this comparison would take a lot less time in hexadecimal than it would take in binary. In decimal, it would take less time, but I would feel like you would need some sort of transformation from binary out of this priority encoder into decimal. So that could also be a complication. So hexadecimal is already just super sweet to work with, and it's super fast. So that works here. Anyways, that's all I have to say. I hope you enjoyed, and thank you for watching.